Hello, everybody. Happy Friday, and welcome to today's webinar on turbochargers. I am Amanda Harmoning. I am an admin assistant here at AERA, and I will be helping moderate today's event with my colleague, Rob Monroe.
Hey everyone, Rob Monroe here. I look after membership and technical development over at AERA. Now, Steve Fox and Chuck Lynch, they're two techs here at AERA. They do the Engine Professional podcast. And right now, they just finished recording episode number 9. It's going to be on engine break-in procedures. And it's about 30 to 45 minutes, and it's excellent. It's got some really good insight on some business tips, technical tips, what's going on in the industry. So I would encourage you to log on to you can go to our website and go right into all the podcasts there to have a listen, as well as you can subscribe from your favorite podcast hosting site. So that's a good one for you to go to. And again, just more information out there to learn.
Okay, in part 2, we want to cover understanding failure analysis, as well as understanding OEM versus alternatives to OEM turbochargers. And another important dynamic is determining the correct replacement unit. And then we'll touch on some basic troubleshooting areas. First of all, let's talk about failure analysis and turbochargers as it relates to engines. And I like to call the turbocharger as the heart of any engine that it's applied to, for the simple reason that the turbo has all of the engine's gazintas and gozoutas. I think I spelled that right. It sees and handles all the air that enters the engine. It sees and handles and experiences all of the engine's exhaust. And it lives on the engine's oil, just like the blood in your veins. So if any of those areas are amiss, the turbocharger will tell you that if you're able to do an informed autopsy on a turbo cadaver. In the area of turbocharger failure analysis, 80% of all failures fall into one of 4 categories. Foreign object damage, FOD, is not unique to turbos. FOD affects all different kinds of things, including the entire engine. Then you have contaminated lube oil, a lack of lubrication, and high exhaust gas temperatures. So while there are literally dozens of other types of causes for failure, due to this being the 80 percentile and limited time on the webinar, we're only going to talk about these 4 here today. But the point of all of this is that turbo failure analysis can provide great early insight into the potential for engine problems. So those of you on the webinar who are engine rebuilders or remanufacturers, if you have a turbocharger that's failed, doing the right diagnosis can give you insight into what could be coming down the line for that customer's engine in the case of, say, contaminated lube oil. That could be an early precursor to larger engine problems down the road. So let's look at a turbocharger where this is what's called either the cartridge or the CHRA, center housing and rotating assembly, with the housings removed. Left side, the compressor, right side is the turbine. And so the inducer of each wheel is where the gas is induced into that wheel. The compressor wheel at the center and the turbine on the tip area. So on a foreign object damage, this is the easiest to determine with a minimum of training, because if we look at 4 different compressors here, all of which that have failed by various foreign objects, the leading edge is damaged, and there's no other form of failure where the compressor wheel is intact, okay, and the leading edges are damaged, where it's clear and obvious that it has tried to ingest something. In this particular case, it was a bolt. A loose washer stayed in there long enough, and the operator clearly just continued to drive it, and it wore the compressor wheel away. A shop towel won't be as abrasive as a bolt because it's just going to bend the wheels back. And a loose bracket can also take place and be ingested. But the point here is you do not need to disassemble the turbo. You can look into the compressor cover and the compressor's inducer area, and if you see leading edges that look like this, foreign object damage, slam dunk, no further diagnosis necessary, other than what caused it, so that you look upstream of the intake to make sure that any remaining debris doesn't fail, again, the replacement turbocharger. That's not as uncommon as you might think. So that's the value of it, is to know that that's typically not a warrantable failure, but also if you're servicing that turbo and you didn't go upstream to eliminate that, then the question is in the customer's mind, who's responsible for that second failure? So that's what you want to make sure that you understand and maximize the quality of service for your customer. On the turbine side, depending on the design of the turbine housing and, of course, the size, you could look into the exducer of the turbine housing and possibly see the tips. But probably 75% of the time you would need to remove the turbine housing, and then you're looking at the inducer of the turbine wheel. And that can be most commonly like a valve fragment, or somebody who's rebuilt the turbo and maybe what's called a little spaceship, part of the deburring medium that some people use in turbine housing, deburring and cleaning, could have been left over, but it's commonly a valve fragment. So when you see a foreign object damage on a turbine like this, then you really want to question what's going on inside the engine. It might be wise to do a leak down test of that engine. And if it is a valve fragment, because commonly it won't be found if it's a small fragment, it'll end up stuck in the muffler someplace, and good luck finding it. But doing a leak down could give you insight into the engine's integrity. And in that case, it's certainly not the turbo's fault. There's another problem going on. Contaminated lube oil is an interesting failure where if it's contaminated lube oil, then it's systemic. And as such, you will see the classic scoring on all bearing points throughout the turbocharger. Not necessarily present with heat, but in the thrust bearing, and there are two sides to this thrust bearing, you'll see the scoring. And here is one of those full floating bearings where the shaft is rotating in relationship to the ID of the bearing, and the bearing itself is rotating in relationship to the bearing housing. And you'll see consistent scoring systemically, and that will tell you that the lube oil has small contaminants in there that are abrasive. That type of failure will commonly lead to excessive clearance in the bearing here that cause a wobble between the turbine shaft and the bearing, and you lose the stability of the rotor, which can then cause either the compressor or the turbine to come in contact with its respective housing. So when you see such a failure, taking the turbocharger apart and finding this evidence will tell you that the contact of the wheel to the housing was secondary to this being the cause. And the wheel to housing contact is a symptom, not cause. Now, lack of lubrication is interesting to where, similar to systemic contaminated lube oil, if you see evidence of high heat throughout all of the bearings, you can suspect an inadequate supply of lubrication. So you would want to look at the pressure lines Has that been crimped? Is there another problem? Is it undersized? Has somebody changed something? Because there's a lack of lube throughout the turbocharger. Now, you can also find, say, a thrust bearing that looks like this, or just the journal bearing that looks like this, and the rest of the turbo looking fine. If you have, for example, a journal bearing on just one of the two journal bearings evidencing high heat or lack of lube, that could be, rather than systemic to the whole turbocharger, a problem in an oil galley. On rare occasion, during manufacture, there could be a broken off drill bit in an oil galley, causing a blockage to that particular point of the turbo. But more commonly, it'll happen on the turbine end, where during what's called a hot shutdown, the oil that's left over in that galley sits there and cooks, and it creates coke. And just like cholesterol in your arteries, that happens repeatedly over and over, and it continuously constricts the oil feed to that bearing, and it begins to superheat because the oil is not a high enough flow to transfer enough heat away from that bearing surface. In a high exhaust gas temperature, you have a number of things to look at. One of the things that you want to be very careful of is looking at the inducer or the tip of the turbine wheel. It can look like foreign object damage, but if you look very closely, and possibly with the aid of a very simple 10 times magnifying glass, you'll see evidence of where the tips have been molten, okay? And if it's high exhaust gas temperature, then that won't necessarily be a standalone, because high exhaust gas temperatures don't fail the turbocharger rapidly like a foreign object does. It will happen over a longer period of time. And that means that cracking of the turbine housing and severe erosion of the divider wall and or discoloration on predominantly the turbine side, these will be companion symptoms that will help with the proper and accurate diagnosis by them all being collectively evidentiary to what the real cause of turbo failure was, of high exhaust gas temperature. Now, what caused the high exhaust gas temperature? In a diesel, for example, can be just simple overfueling. More fuels, more horsepower, and the guy doesn't care about black smoke. It could also be a series of injectors that are not spraying properly, thus atomizing the fuel and causing a lot of afterburn in the exhaust stream itself, where what's going on is the exhaust system and the manifold is an extra combustor without adding value. It's just damaging the turbo. Now, all of us in the service aftermarket have heard OEM position claims that OEM is best, but let's set that aside for just a minute, because all of us know that there are many components out there that are manufactured or remanufactured in the automotive aftermarket and are certainly equal to, and in some cases even higher quality than what's found on the OEM side. So the OEM differentiation in the turbochargers takes on a little different meaning in my mind. The new turbocharger replacement market is certainly in an ideal condition right now, and because of that, it's attracted a lot of players from various areas of quality. And because of these tens of thousands of turbochargers that are being serviced, and many more to follow every year, that's attracting a broader and a broader crowd. And you know, most independents understand the cheaper offshore domestic reman units are not necessarily higher value. And in the case of gasoline applied turbos, I believe OEM has more meaning than virtually any other engine component. But you may ask, why? Well, consider the environment that a turbocharger lives in, and the fact that there is not a turbo engineer on the planet that can look at a nice, clean turbocharger just taken out of the box and determine with the naked eye the metallurgical integrity. Is the turbine housing made from the right material? Is the turbine wheel made from the right material? Is the compressor wheel made from the right material? What are the internal dimensions of the oil clearances? Are they correct? Whether the compressor cover and or the turbine housing will contain a burst. I was personally fortunate enough to run a burst stand right out of college, and I've blown up more turbochargers intentionally than anybody else I know. And the reason that's done as part of the engineering spec that all of the legitimate OEM turbo manufacturers have, that's just one of many of the engineering specs, that turbine housings and compressor covers must contain a burst in the event of a wheel burst, and they will burst, and they can be lethal. Can you tell with the naked eye that the wheels are properly balanced for long-term life expectancy? Is the compressor and turbine efficiency adequate for proper engine operation? You can't tell that with the naked eye. And whether the manufacturer has made any shortcuts and compromised operational integrity by any number of shortcuts that can be made, such as there's probably very few people on this phone that understand that turbine wheels that are threaded, the turbine shaft is threaded at one end to hold the compressor wheel on. Well, a shortcut is to cut those threads, but a high quality OEM turbo manufacturer will roll the threads on. And the rolled threads do not interrupt the grain structure of the turbine wheel, and that allows it to have a higher tensile integrity to hold and maintain holding the torque applied on that turbine shaft. So don't fall prey to looks, unless, of course, you're buying pretty umbrellas for tropical drinks. So again, to summarize this in another way about the OEM differentiation is to think about the environment that a turbo lives in. It's like a watch that has to live in the stream of a jet engine. You know, bearing clearances go down to 4/10,000ths of an inch, which is 7 times thinner than a human hair. The turbo itself can accelerate from 50,000 RPM to 200,000 RPM in less than 2 seconds. And an F-16 takes 3 seconds to do that. The rotor group can rotate as high as 350,000 revolutions per minute, where a Boeing 787 only reaches 14,000. I think my girlfriend's hairdryer only goes to like 9,000. The turbine inlet temperature can be as high as 1,900 degrees Fahrenheit, and window glass melts at 1,800. The G-force that a turbo has to live in can be as high as 25 Gs, and fighter jets only go to 14 Gs. Wheel tip speed in surface feet per minute, the outside diameter, can reach Mach 1.7. And the average compressor flow doing all this is 20 cubic meters, which is roughly the capacity of a utility van, and does that every minute. So when you think about it, cutting a corner on a device that's this expensive isn't saving money. That's not the place to look outside of the OEM, in my opinion. So let's talk about some basic troubleshooting. Is a turbocharger a cause or a symptom of a problem when there's oil leaks? And is there a simple way to determine if the turbocharger has failed? Well, again, remember, there are no oil seals in a turbocharger, but it's not uncommon to find evidence of oil around a turbocharger that shouldn't be there. But it's also natural and instinctive to think the turbocharger's leaking oil. Well, that's maybe more a symptom than the cause because of the lack of oil seals. So let's talk about a few things that can produce oil in and around the turbocharger. The oil drain line on a turbo is supposed to drain back into the pan above the oil level. Okay, so that's one area. But if you find evidence of oil out both sides, you could have a restriction in that drain tube, and that restriction can be impeding the oil flow, especially at higher speeds. So the oil builds up here, floods the drain cavity, and then those flinger sleeves that remove the oil from the area of possible leakage become overwhelmed, and oil can be basically pushed out. That will also more easily happen at moderate speed and not as much at higher speed, where the gas pressure on both the compressor and the turbine side will tend to counteract that. If the engine is severely worn, or there's a problem with the crankcase ventilation or evacuation system, the pressure that can build up in the crankcase with the oil drain back exposed to that air, that pressure can come right up into the drain cavity and basically cause an increase in pressure in the drain area. And again, at lower speed, can push some of that oily residual air past the seal rings. That can be another problem. So a crimped oil line or excessive blow-by on an extremely aged engine. And then, of course, as I mentioned in the first, if the drain is located below the level, that could be due to overfilled crankcase. So everybody knows you don't want to overfill the crankcase, but this is yet another reason why that can impede the oil drain back rate out of the bearing housing. One other point, for those of you who are doing any performance or retrofits, if we looked at the orientation of this oil drain from another 90-degree perspective, the drain line should not be more than 20 degrees left or right of perfectly vertical. Otherwise, you're impeding the oil drain back characteristics. So while it's not in this slide, if you find an oil leak problem and that oil drain is emanating out the bottom, but at say a 45 or 90 degree angle, that's the problem right there. Troubleshooting. There's a lot of elements involved with troubleshooting, but what's a simple way to determine if the turbocharger itself has failed? This takes a little bit of experience, but not a lot. There's a couple of things I want to share with you. With the engine off and cooled, remove the inlet air connection if you suspect the turbo might be a problem, and reach in to grab the compressor nut. And you can push in and out for axial force and wiggle back and forth for radial motion. You should feel if the turbo is in good shape and has its oil film in there, little to no end thrust. There will be some, but it will be tough at that angle to feel anything. And then it should clearly rotate freely and smoothly. So if it's rotating freely and smoothly, you can't sense any axial or radial movement, or extremely minimal. Chances are the turbo's fine. Now, another important point in this consideration is when replacing a turbocharger, know that many turbochargers are built dry, meaning they do not use assembly pre-lube like you would when you're assembling an engine to lubricate all friction points during initial startup. They do this because after the rotor assembly is torqued and in place, there is a quick measurement they do of what's called a tilt study, and they know exactly, if built dry, if all internal dimensions are correct, they know exactly how much that will wobble. But then when you assemble the turbo, stick it in a box, and then somebody at the other end of the shipping takes that out and wobbles it like we just talked about, it sounds rather rattly and loose. and they wonder if that's a problem. It's not a problem, but it reinforces that it needs to be pre-lubed. So after you mount the turbo on the engine, but before you connect the oil inlet line, it's advisable to put some clean oil into the intake and simply rotate it a few turns. It'll only take about 30 seconds. And you'll feel the internal clearances tighten up from the gravity feed of the oil. And that will save some initial startup wear, because while the turbo won't build boost, it will begin to rotate at a fairly fast speed just starting the engine up. So pre-lubing a replacement turbocharger is the thing to do. Now, this is far too busy of a troubleshooting guide to cover in this webinar, but I just wanted to show you that this does exist, that has the probable cause and the potential symptoms and troubleshooting of a turbocharger. And that particular chart is on page 152 of the book Turbo Real World High Performance Turbocharger Systems. Additionally, there's much more on the failure analysis in this book. I don't care much for the author, but he does a pretty good job on the failure analysis side of things, and it's the only book I'm aware of that is available in the open market that dedicates a whole chapter to failure analysis. Another piece of reference material that I think would have value to everybody and is available to everybody free of charge is the ATG. That is the standard automotive turbo guide. That is the industry's most comprehensive guide to high quality replacement turbochargers. It's designed, created, and maintained exclusively by Diesel USA. And so it incorporates those 5 worldwide major turbocharger manufacturers and all the applications that they're on. And with the graph that you saw on the expansion of the market, we're updating that right now on almost a monthly basis. So if you would like a copy of it, we'll tell you how to get a copy of that. This is what it looks like. It's available both in hard copy, printed form, as well as interactive digital. And on the inside, it is organized in alpha form by brand, and then engine and model of vehicle. And it will tell you if there is an available replacement unit new or reman, or even if there is an upgrade available for that application. And then there is even a section in the back you can go straight to that references performance upgrades where available. Now, in some cases, there are turbochargers referenced for an OEM application that isn't necessarily the brand that was on that OEM to begin with, but we'll reference it because it comes from one of the OEM manufacturers. So that if brand A makes a replacement unit for brand B on that application, if brand A and B are both OEM manufacturers, the integrity of that turbocharger is high enough to have confidence in, because these manufacturers do not vary their engineering specifications based upon whether that turbo is destined for the OEM assembly line or the aftermarket. So the consistency of quality of engineering and quality control and manufacturing are intact across both their OEM and aftermarket channels. One point important reference, this is extracted from the inside leaf of the ATG, and it says the best way to ensure that you have the most accurate, up-to-date replacement turbo is to use the part number cross-reference. And what that's referring to is that 80% of the time you can look up in the ATG your make, model, year, and go across to the application, and that will work 80% of the time. And in other computer references, it will do the same thing. However, there are mid-year updates and changes constantly being made. And so the best telltale way to identify the proper turbo is to use the ATG and identify the part number on the turbocharger being removed that crosses over to the correct field service replacement turbocharger for proper fit and performance. So how do you get the ATG? Again, it's available in both printed and digital interactive forms. It's real easy. Whether you want one or the other or both, simply send an email to atg@dieselusa.com. What we will do is we'll put you in a database, and the ATG is typically updated about every 90 days, but here in the last 6 months, it's been updated about every 30 to 60 days because of the rate of change of available turbochargers. And we'll send you your copy, and then you're on the list, and as we do updates, we'll automatically update you so that you have the latest information available in the turbocharger replacement market. And that basically concludes part 2. Rob, we can take questions from here.
Sure. Thanks, Jay. Yeah, excellent presentation. Very, very well done. Like you mentioned when you first started, there's a little bit in there for absolutely everybody, whether you're just new to turbochargers or you've been working on them for years. There was some great information there. So Jay's information is on screen there. They've got their web address as well as their email there. So if you have any questions, by all means, I know they'd be more than willing to help out. So just go ahead and contact them. As well as any questions we don't get to today, if we do run out of time, I will forward these to Jay, and like I say, one of us will get back to you to make sure that all questions are answered. So, Jay, here is a couple questions for you. This gentleman's asked, are closed isolated oiling systems gaining popularity in production engines, or is this proved to be not economical and reserved to only extreme performance or failure, not acceptable applications like certain aviation or marine type applications?
Wow. That's not really turbo specific. That's an engine development specific. And I don't know whether he's referring to dry sump versus wet sump, or I'm not really sure I understand the question well enough or can legitimately respond to that question in terms of engine development. What's going on there?
No problem. Yeah, no, we'll make a note of that, and I'll send that one to you. We'll ask for more clarification as well, so we can get that answered.
If he'd like to expand on the question, then we can handle it offline in a different way. But I'm not sure I understand really what the point he's driving at.
Sure. Yeah, no problem. Another question. This gentleman has mentioned that they often see data that claims diesel turbos have much lower EGT limits compared to gasoline turbos. Is that true?
Yes. In people that know engines know that a diesel engine exhaust, and we're not talking about performance engines, we're talking about just regular OEM applications. The diesel engine exhaust stream is typically much lower temperature than is a gasoline engine. And as such, there is commonly a shift in the metallurgical property in the turbine wheel and the turbine housing. It's common for the alloy GMR 235 to be used in diesel turbine wheels, where Inconel 713C is used in either high-performance diesel applications on higher temperatures or automotive applications. And the same issue and concerns that are temperature-related actually grow out to the concerns with variable geometry. A diesel running lower temperature is more successfully running variable geometry than a gasoline engine on the higher temperature with all those moving parts in the exhaust. But it's the idea of using high temperature and variable geometry for gasoline applications is more about affordability than feasibility. You'd probably require the use of things like cobalt which would drive the cost of the turbo exorbitantly higher. So the technology and the metallurgical capabilities exist, but the practicality from cost effectiveness is the challenge.
Okay, all right. Another question here for you. What are your thoughts on spraying water or methanol into the turbo to keep the charge temperatures cool? They mentioned that Volvo implemented this idea decades ago. It was abandoned by OEMs, but important performance cars seem to utilize this. Or drilling tapping into the turbine housing itself so it doesn't hurt the fins.
It's been done successfully. That's the best way I can answer that. That's a very, very isolated, unique application. The area of exposure I have to that is in the tractor pull arena, where you are experiencing incredible levels of boost in excess of 100 pounds. When you're doing things like that, it'll make sense to do that. But I wouldn't advocate anybody doing that. There's also a lot of risk associated with that. It's a good way to destroy the engine too if you don't meter it correctly.
All right. Are there any performance benefits to rear-mounted turbos instead of engine-mounted turbos, other than being able to potentially utilize a larger turbo?
I'm going to follow the traditional application engineering community that will basically tell you, and I know the turbo system manufacturer that we're referring to here. I don't care for it. Putting the turbocharger rear of the engine of the vehicle is not ideal. It will work. There's no doubt about it because it has worked. And it makes sense for a simpler kit installation for both the manufacturer of the system as well as the simplification of installation. However, if you go back to the fundamental basics of what the turbine is trying to do, it's trying to convert energy present in the form of heat and pressure into mechanical energy. You've lost a lot of heat energy between the exhaust valve and the tailpipe. So that also exposes the turbo to a lot of elements it would not otherwise be exposed to either. I would be worried about temperature sensitive components sitting in the trunk. There are coach applications that haven't properly insulated a turbo, and you can find fires on YouTube. I'm not saying that this type of system would cause such, but it's outside the norm of what most people in the turbo community would see as appropriate. So I'm only expressing my opinion. I'm not stating this as fact, but I don't care for the rear mount systems.
All right. Okay. So Jay, this one's kind of in relation to oil. Same thing. You can let me know whether you'll be able to answer this or not, but they're asking, what oil viscosity do you recommend for like a 1VD-FTV 4.5 liter twin turbo diesel, especially Africa climate conditions? 15W40 is becoming obsolete. Would a 5W40 synthetic or a full synthetic engine oil work well for this application?
Yes, it would.
Okay.
Yeah. When turbochargers go through what I've referenced, the ES series of specs, one of the things that they do is look at a variety of different scenarios, from shaft motion to bearing clearances to imbalance limits, including changes in oil. So following a manufacturer's recommendation is fine, but you might have a turbocharger application on an engine that OE manufacturer doesn't recommend. Synthetic oil is fine. In my personal vehicle, turbocharged, where you have a higher pressure, I always use a type of oil that has the additives in it that sometimes are a little more expensive and can be harder to find. Castor oil makes an excellent competition type oil that is for high BMEP engines. That's always a good choice. So in South Africa, that's typically a warm climate. Yeah, you want a full-bodied oil, and a synthetic is fine. It will maintain its integrity. But in my opinion, that should be fine.
All right. Okay, so this gentleman's question is a little bit more referring to marine applications, but they're asking, can you tell a little bit more about air temperature differential or ambient versus turbo compressor inlet that can affect overall turbo performance and durability?
Okay. I'm trying to determine in my mind what they're trying to achieve here, but let me start out principally with, okay, you're going to have ambient temperature, and in the world in which we live, if you're going to be out on a boat, I'm going to assume it's a pleasure boat and not commercial marine, it's probably going to be 60 to 100 degrees outside. And the compressor, the temperature of the compressor discharge will be really a function of the boost pressure, just like the compression in the engine, where if you have a high enough compression ratio, you can introduce diesel fuel and it will combust it because the air temperature will rise to the kindling temperature of the fuel. It's not uncommon for a 15 to 20 pound gauge boost pressure to see anywhere from 300 to 450 degree compressor discharge temperature. Now, the question becomes, isn't that awfully high for intake? Yeah, when you get past about, and I cover this in the book, when you get past about 7 pounds of manifold pressure, it pays dividends to aftercool the compressor's discharge before introducing it to the engine. For every degree lower of temperature intake to the engine, it drops the exhaust gas temperature a corresponding 1 degree. The engine derives its horsepower by the pressure rise, not the temperature rise, but the pressure rise from combustion. So ideally, you want to have the lowest possible intake temperature, and above 7 pounds pressure, you should consider a cooler. And again, not only does that help the engine respond with higher air density, but it also lowers the exhaust gas temperature degree for degree.
Okay. All right. Jay, we've got a couple people asking, this is going to go back to an oil question again, and a few of these questions are kind of related, so I'm sure you'll be able to answer all of these all in one shot here. But basically they're asking, are there any oil additives that could benefit a turbo's life and performance, you know, such as maybe zinc, ceramic, or is running synthetic oils with an ester base stock? What's your opinion on that?
I don't think there's magic in a bottle. The turbocharger, as designed, if you're using a quality engine oil that contains already the additives for performance engines, the turbo is resilient enough to using a quality oil. I know of no one in the turbo community that swears by a specific additive that really helps the turbo. It doesn't spin faster, doesn't make it longer. You've got turbochargers lasting 1,000,000 miles with just making sure that the oil is well filtered and changed regularly. So I'm not a big advocate of a lot of additives. That's just my opinion.
Okay, all right. Couple more questions, everybody, and then what we'll do is, I know everybody's busy and we do respect your time and everything. Any questions we don't get to, like I say, we'll forward those to Jay. But Jay, you did mention in the part 2, you were talking about one of the failures was like a hot shutdown. Does there need to be a cool down period for a turbo before shutting the engine off?
That's a great question. Yes, there does. And the longer you've run the engine hard, the more you need to consider it or lengthen the cool down period. because what happens is if you're running the engine pretty hard, you're building up a lot of heat, and that turbine housing acts as a heat sink, and it sits there and glows red hot. You pull off the highway, for example, or off the drag strip or back road, and you shut her down for whatever reason. Then what happens is the oil stops flowing through the turbo, and the turbine housing just sits there without any cooling gases, and that heat is given the opportunity to migrate into the bearing housing. And with the oil, the residual oil sitting there, not moving, it just sits there and boils and cooks and cokes up. And that can lead to, if done over time, can lead to oil starvation due to restricted oil galleys like we talked about before. So turn that back around to what should you do before shutting the engine down. Again, it's a judgment call. There's no magic, but letting it idle, if you run it medium hard for 30 seconds to 60 seconds. If you've been running it extremely hard, maybe let it run for a couple of minutes before you shut it down, and that will give the turbo an opportunity to dissipate the excessively high heat. There are devices out there that act as an accumulator that will continue to feed pressure oil after shutdown. That's a good idea, but if you practice a normal cool down, it's not necessary to use those.
Okay. Yeah, that's a good, honest answer, Jay, because someone that sells turbochargers, you could have said, no, just shut her down. It's all good. We could. So yeah, that's a good answer. Very honest, for sure.
We don't. There's enough turbos out there. We don't need to falsely sell a single turbo. There's enough turbos out there that just legitimate service is all that's necessary. The objective of this seminar clearly is education. So,
right. Yep. The Just Gentleman's asked, any comments, good or bad, on the draw-through systems in which the carburetor flows through the turbos or to the turbos? Any advice for power or longevity on those?
Well, that's an excellent question. That's a very specific question. That somebody wants to know the classic blow through or pull through. The reason most application engineers or just high-end hot rodders have chosen the draw through is because a carburetor will sense volumetric flow and meter the fuel according to the volumetric flow through the booster ventures. But a carburetor can't sense air density. Okay, so a carburetor circumvents computer-controlled fuel delivery, and so you have to rely on that manual analog metering capability. And so that basically addresses the boost enrichment necessary when you put the turbo downstream of the carburetor. However, that submits the compressor cover of the turbocharger to vacuum in a part throttle situation, which means that you either have to do what's called a vent seal, which is a lost art, and that's where you vent the area underneath the insert of the compressor in the area of the flinger sleeve to atmosphere, so that you don't suck oil out, or you use the old-fashioned carbon face positive oil seal that was used in the pre-1987 era, which lowers the turbocharger's efficiency because it's a drag on the wheel, and it is a shortly lived item, but it is a positive oil seal that keeps you from sucking oil right out of the turbo. So if I was going to do one, I'd probably do the draw through because it simplifies the fuel metering for boost enrichment.
All right. So Jay, we got one more question for you. Again, we're trying to respect everybody's time. It is Friday afternoon. There's probably some shops out there trying to get some work out the door. Like I mentioned, any questions that we didn't get to, we'll get those over to Jay and we'll get those answered and get back to you on that. Jay, this gentleman's asked, is the rebuilding of a turbocharger complicated, or can someone like the do-it-yourselfer do it, maybe in their home shop or home garage or something like that?
It's hard to recommend that it can be done in your garage, and there are a couple of reasons why. First of all, when you go to rebuild it, do you have the tools? Do you have the proper kit? But most importantly is, do you have the ability to verify the balance of the wheels? Compressor wheels and turbine wheels are individually balanced on two planes. So let's take a compressor wheel. You balance the nose and you balance the back wall to get a dynamic balance. But typically in rotor group, in turbine frames that use, say, under about 3 to 3.5 inches, it is also done on a core balancer where you have balanced each wheel on two planes. Then you assemble that center section, the cartridge or the CHRA, whichever you wish to call it, is then balanced as a rotor group. That's an additional step that there's probably no one connected on this webinar that has what's called a core balancer in their garage to balance it at high speed. Because typically the smaller the diameter of the rotor, the higher the rotational speed it will see, and therefore the more delicately balanced it will need to be. The closest you could really productively do if a person wanted to rebuild is a partial by servicing a turbocharger with that cartridge or CHR assembly, where the removal of each end housing can be done, and then replacing that center operational section that comes pre-balanced. Sometimes on smaller automotive applications, those CHRAs cannot even be had. But if they are available, that would be probably the best service option that you could recommend safely done in somebody's garage.
Okay, yep, so good to know. Well, Jay, it's been a real treat working with you. I know you put a lot of effort, and there's a lot of preparation that goes into these types of presentations, and you helping us educate our industry. And I know on the tech line, we're getting more and more turbocharger related questions. We're seeing more turbos out there, obviously, as well as, and of course, with that goes the failures. And you've kind of definitely opened up my eyes, and hopefully everybody got a good taste of just what goes on within that turbocharger. So I thank you. Great job. And thanks again, Jay. Much appreciated.
I enjoyed it. Thanks for the invite. And I just wish everybody well.
Super. Thank you.
And then lastly, you'll see our contact information is listed there. You can reach anyone at the AERA team at 815-526-7600. And then my email and Rob's are there as well. Go ahead and reach out to us if you have any questions or follow up on this stuff. We're happy to help you. Thanks again for taking time out of your Friday. We appreciate it, and we hope you all have a great rest of your day.